we're going to finish chapter 2, which really has all the component of running a machine learning project. And then for the next two sessions, we'll focus on chapter 3. To a big extent, it's really a repetition of what we did in chapter 2. The nice things about chapter 3, not only that it is a good review, it is really has a good case, and it means I will show it. Okay, so that's really will complete our course.
Okay.
Make the requirement in such a way that it will not be a technical. I most likely will provide you with most of the material you need, but I do want a nice write-up of what is really being done and what are the results, okay? Okay, because I really don't expect that you'll be active writing code in this stage. I don't think you have that. It won't be really fair to do that, so that's what we will do. Okay, so let's see, let me just really just glimpse a little bit on chapter 3. Okay, if you see chapter 3, it's really a nice case in which, you know, people have kind of worked on this kind of a problem for many years. You know, when people have a handwriting and you would like to identify exactly what the number is. So this one, some people would think it's 6, but it is really 5. And you give a computer a lot of those numbers, like from 1 to 10, from 0 to 9, and you train the computer to identify numbers, okay? And then when you give him a new number, you will see if he can identify. So this is really what the input going to be to the computer, and we will talk how to prepare data like that to the computer. And it has to really, based on different zeros, even if it would get a different, slightly different, somebody would write it slightly different than 0, it will still be able to identify it as a 0. That's pretty cool. Now, the question is, how do you present something like that to the computer? That's what we'll talk starting next week, okay? And then we will see that we will follow basically everything we studied over the course, step by step, so it will be a really nice review or kind of review for the exam, review of the material, and redo. And in fact, in my opinion, as I said, it's even in the course Business Intelligence, repetition, it's very important in machine learning and computer science. You don't review, you forget, it becomes to be totally lost. And then we'll add some criteria, we'll talk about some criteria today of what is a good model, and we just extend it a little bit with some more stuff, precisions, and all of those stuff. And that's what will be the end of this course, okay? So that's coming for the next 2 sessions, not today. Today I'm gonna finish chapter 2, and that's gonna be for the next 2 sessions. Then we'll have last session, we'll do some review for the exam, okay? So let's start. Last time we got to preparing the data for machine learning. If you notice, really so far we have gone through a lot of data exploration. I mentioned that it's very important to, you know, it's very important to view the data, see the data, look at the data, look at the correlations, and we did all of that stuff. That's really very important. Many times people skip that, they end up with garbage. You know, looking at the data, you know, just here, even without anything, so you can tell there's a big, you know, population around this area, a lot around here. And then when you get into colored one, okay, like this one, you can tell that the high prices are close to the ocean. You know, you don't really need an algorithm to see that, but a nice plot like that really does a lot of work. And we talked about a lot. I warned you about the meaning of correlation last time, and we saw a little bit when we talked about all those charts. Please do review what we did in the previous session. It's very important. We talked about this phenomenon that's happening in a lot of data. This can destroy many times. You really have to remove them or just ask for complete true data and not data that were chopped by someone. Notice we spend so much time on data preparation, extremely important, very, very important. We talked about correlation, then we talked about adding new variables, which is also very important. We saw that bedroom per room, it's very important, much more important than just bedroom itself, because it's more correlated with the median value, house value, okay? And then it's kind of funny, it's like we're starting all over. Well, data preparation for machine learning. So what we did so far. Well, what we did so far is what every statistician should do before we start. Now we're preparing the data to work with tools specifically built for machine learning. As I mentioned, I made a special component for you, for machine learning. I call it basic machine learning object, which include a lot of the stuff that we talked about during the semester. So please do review that. I'm not going to ask that higher level, as I mentioned before, but I am going to ask for specific functions. What do we use them for? Okay, I'll reopen it one more time. I'm not going to ask you for detail, but I am going to ask, for example, why do we use training test split? We're splitting the data to training database and a test database, and I'm going to extend the discussion today. Okay, we have a function called save figure. Well, if you want, go ahead and learn how to do that. I strongly recommend. I am not going to ask you in the exam, but I do really require that you know that you can make a function that can save a plot into the hard disk and you can read it anytime you want. So I do really require that you know what the functions of what those functions do, but I'm not going to ask for the detail too much, okay? At all, in fact, okay? So let's go back to here. So we started last week. We talked about when we're preparing the data for machine learning, stage number one, what do we do when we realize in our database we have missing data? Then we said there are three options. One is just remove every record that's missing some data. Options two is just remove any column that has missing data. And honestly, I don't think either one of those two is a good idea because you're losing a lot of information. And then there is the third option is using what is known as imputation. Here we saw how can you do it manually, but there is a really nice component, and we utilize this component to start learning how the scikit-learn library is really built on a nice structure. All the components have very similar structure. And as we go, you will see how very quickly you'll get the idea. So the first one we use is imputer. And the objective of using imputer, you know, it's like you're bringing, by the way, in Python, this is the library and that a sub-library, and I'm importing an object, and the object is called imputer. And in objects, as we studied in the beginning of the semester, we create an object. And the object, we call it imputer. This is the name we gave to an instance of this object. By the way, it takes one parameters. If you remember when we studied object-oriented, we can put parameters to the object. And here we told these objects, please impute for me using median. I could have written average. I could have written other statistics that I might find, but median is a really good one. It's not affected by outliers like average. So usually people do use median, but again, as I mentioned last time, this is still simple imputer. In real life, they are much more sophisticated imputers. I will mention, if we have time, I will mention stuff that I, in real life, use. And they're really beautiful stuff, but it's too advanced for this class. But just remember, you have an imputer already in this library. You can build up your own imputer, as I will explain today, but I'm not going to require you to do it yourself. Too advanced for this class. Okay, so what do we do in the imputer? Stage number one, the imputer, works only on numerical numbers. That means if I look at the database, let's look at the database. I think I have it here. If you look at the database, okay, and let me see. No, not this one. Okay, if you look at the data,
Amos,
yeah, go ahead.
maybe mute everyone.
I think
Because there is like
did,
a background
let me,
noise.
Let me double check. Hold a second, sorry. Yeah, I did now. Okay. Good. But I think I can still hear you, by the way, but no one else can hear you but me. Okay, so if you have a question, please feel free. Okay.
Thank you.
If you notice, this is our database. We have a lot of columns that are numeric, and one of them is what we call categorical column, okay? And then we said, okay, those numbers we're gonna convert to be ready for machine learning study, and we have to take care of categorical. And then we said the computer doesn't really like word, and I mentioned that in business intelligence course. We usually like these kind of things to convert to numbers. Numbers works very fast. By the way, NumPy array doesn't take strings, or in fact, more correctly to say, it doesn't take combination of numeric and strings. Okay. And usually I never really remembered myself using NumPy array for something that is not numeric. Okay, so we need to take care of this variable to convert it to numbers, still don't lose the information. And then how are we going to convert all the other numbers? And that's stage number one in preparing the data for machine learning. Okay, so stage number one, we remove one column, which is this column. We remove it and we prepare a data frame including only numerical columns. And this one, we're going to look at that by himself. Okay, so that's stage number one. So we dropped that column, and now we're going to work. By the way, if you notice, we have imputer, we created it. We implement kind of really, more correctly to say, we fit the imputer to the numerical data frame, because this one has only numbers now. What it really does behind the scene, it calculates the median for each column. So for each column here, it takes the median for each one of them. Now that's when we do the feed. We also said last time, every one of those has also a function called transform. What do we do then? When we implement I will skip that one for a second. When I do imputer that transform on the same data, all what it does, it really actually, wherever we find the missing data, it puts inside the median of that column. So if there is any column missing any data, it will take the median and will put that number right inside. That's pretty cool that somebody already have done all that work for us. So we don't even have to think about it. This one is ready for you, whoever wants to look at it, and I really strongly recommend. You can calculate by yourself the median, and then you will see when the imputer, after it kind of feed, it has a variable called statistics. And that statistics is the actual median. So you can really compare for yourself, convincing yourself that this is really what it does. But that's really just a nice exercise. One important thing is the imputer, whatever it gives it out as a NumPy array. So if you want to convert it later on to a Panda data frame, you simply just call PD, it's a short for Panda. When we define the pandas, we always say, we give it a nickname as PD. That data frame is just converting the results that coming out from here. You know, this one is really giving me the results. So all the missing data are filled in, and I just get an X. The X is really my huge matrix, all the data, but it's a NumPy array. So just to convert it, I just put it in. By the way, if you look at my objects, you don't really need to remember that anymore. I embedded it inside the objects. So every time you do imputation, it automatically will make it a data frame immediately. That's a nice thing when you really understand programming, okay? So it's already embedded inside here. You don't really even have to think about it. You know, even if you want to remember all of that, no way you can remember. So it's nice to, what I said last time, it's like encapsulating all this code. You do it one time, you know what it does, and you move on and focus on the real work. And that's you will see when we get toward the end of the session today. Okay, so that's nice. So we got a new data frame, but this time, this one has all the data, no missing data. That was one thing we did last time. Another thing we talked about, what do we do is categorical attribute. This is the last column. So one thing is when you look at it, it's there's a few categories. And what we would like to do is, first of all, turn it into numeric. So there is another encoder. By the way, like in Pewter, there is also something called label encoder. And label encoder, in fact, takes a column which has only letters and turn every category to a number. So you start from a 0, 1, 2, 3, as many as categories there are. That's what it will do automatically. And for each row, it will add another column there that will tell me a number, which is really equivalent to the number of that category. That's really what it does. So in another word, if you look at the result, when you write feed transfer, by the way, to remind you, when you do feed, that's learning the category. And when you do the transform, it is really applying its own. What is it implying? It's really generating a long row, a long column. It's like adding another column here, which have 0. For example, let's say this is a 0. The next category would be 1, 2, 3, etc. Okay, so feed transfer does the two things together. And that's typical to all the components of scikit-learn library, which is really cool. I won't go over all the stuff we did last time, just to remind you, he automatically found the classes, he automatically gave the numbers. I mentioned that when he returned the data, okay, we have to reshape the data, because when it gives us as one array, one dimension array. If we want to use it later on, we must transform it to a 2-dimension array. And reshape, it's a little hard function. What this one says, take the data of one array, this is what it created. It created something like that. And I'm telling him, please turn it to 2-dimension array. How should you do it? Please make one column and you decide how many rows you need. In this example, it's very simple. I will have one column and the number of rows, it's the number of numbers I have in this array. So that's really easy. But many times it's very complicated when you're transforming a matrix with different dimension. So reshape, it's not a trivial function. Honestly and frankly, spend some time learning it. I'm not going to be hard on you in the exam. I will prepare you for the exam. And when we get there, I will tell you exactly which kind of level I require for the exam. But for real life, if you really want to be in this field, this is a really good one. It's developing your brain when you start thinking about several dimensions. I mentioned maybe in other sessions, a library called TensorFlow developed by Google. They're using it very heavily on that library. TensorFlow, it's a really advanced algorithm library, beautiful piece of art. And reshape is extremely important. And there you really use 3, 4 dimensions and converting something for several dimensions to 2 or whatever dimension, not a really easy exercise. But just remember for now, when you put a -1, you're telling him, I don't know how many rows will be there. The second one telling him how many columns you want. So if I change that one and I put a number 2 here, it means I'm going to get a matrix, 2 columns, but I don't really know how many rows. The computer will decide. Depends on how many data I have in this row. Okay? Okay. That's general about reshape. That's what we did last time. And now we went into, after we learned that one, we talked about the one-hot encoder. And I explained last time, when we have a categorical, we turn it to numbers. Okay, but that's not going to work because, you know, 0 seems like close to 1 and 4 looks like very far away from 0. But those numbers don't have any meaning. They're just replacement to the text here. So nearby or far from the ocean or whatever categories there are, okay, they might have a meaning as a word, but when I turn them to a number, the number I'm choosing, it's very random. So 4 and 0 doesn't mean they are close in meaning. So to break that one, so the computer won't, the algorithm won't get lost. So we turn those numbers to what is known as one-hot encoder. And again, we have a nice component that does that. And that one, we give him this array, but we have to give it as a matrix. So we did the work inside here. And what it does, it really turns it to a matrix that, since we have from 0 to 4, by the way, there is only, how many we have? 1, 2, 3, 4, 5. There's only 5 categories, meaning it's 0 to 4. So it is going to turn this long array, one-dimensional array, into a matrix with 5 columns. Every place, if it is a, let's say if it's the first category, which is a 0, it will put in that record the number 1 in the first column. If it is, for example, number 4, it will put a 1 in the last column. So this is really equivalent to number 4. This is equivalent to number 0. This is equivalent to number 1, okay, etc. So it kind of, it putting a 1 in the column, in the column, which the number of the column would be exactly the number in here. So if I have a 3 here, it means in the third column, put a 1. So a third column, it's 1, 2, 3. This is the third column. In fact, it should be really, if I wanted number 3, I would put a 1 here, okay? That would be equivalent to number 3. When you present this data to a lot of the algorithms, it's breaking the links that 0 is close to 4. Because in many algorithms, if you just plug those numbers the way they are, the algorithm will think that 0 is close to 1 and infer many things it shouldn't. By breaking it to one hot, it's really breaking that link. Okay, I won't get into the whole things. It's really going into a real statistics, which is beyond the scope of this course. Okay, so the nice thing is all this process of encoding, categorical, turning them to a hot, one hot encoding. There is a nice component called label binarizer. I really never know how to pronounce it, but I know how very well to use it. Don't get confused. It has nothing to do with binary per se. It does because it's turning everything to 0, 1. But the key point is, bottom line, I will give him a column, it will give me this array. So instead of doing the whole work that we did before, I just create, again, from the same library, I have a nice component, and that component, I just put in the column, and automatically will create all these metrics. And that will be extra variables into my algorithm. So what we're gonna end up, in, when we look at the data, all of those are numeric data, we have it separately. And this one going to be turned into 5 columns, replacing this text into 1, 0, 1, 0. All those 5 variables will be added here instead of this column. That's pretty cool. And if you studied in statistics, the dummy variables, it's probably remind you that that's really what you do in regression when you have dummy variables. It's really one-to-one, exactly the same stuff. Okay, good. So now that we have these metrics, and I won't go into the technical stuff, in fact, is returning the data in certain way, and if you want to really convert it to, instead of sparse to regular, you can go ahead and read. I won't really hunt you on that one. The only important for me that you know there is a nice component that takes categorical variable and transform it to a one coding or one hard coding, okay? That's all what I really want you to know. How to implement it, we'll leave it to another time, okay? Finally, I would like just to mention, again, I won't require you to do that, for example, if you have some ideas how to convert the data, and there isn't any component in this library, really famous library, but let's say it's not there, okay? In fact, we would like to, if you remember, we added some variables, you know, like a household per room, okay? Or rooms per household, if you remember those ones. We took one variable divided by another variable. How about if you want to make your own component that does it automatically? And there isn't really one component, so you can build up your own. So custom transformers, it's when you're building up your own component to work just like any other component of this library. And in a minute, we'll see how important it is to build it according to the rules of building components. Again, I'm not going to ask you to do that. It's really too advanced. If you have a good eye, you will see we inherit from two objects, okay? And those two objects, we have to kind of write our own two functions, feed and transform. Usually the feed is very simple, but the transform, it really is, again, too much for a course of 2 points. So I will just tell you, there is a function. In this case, we implemented it to do the extra variables that we wanted. What do I mean by that? If we look at the variables, rooms per household, yeah, okay, we're really taking the number total rooms divided by household, by this column. We take this column, we divide by this column. That generates another column. And we would like it to be automated. So we can write our own component, and here is the instructions how to do it. And then we can use this component. Instead of doing it manually, I can just implement that component. In order for it to work just like the imputer, the one-hot encoder, there's some rules of how to build it up to be in line with all other components of this library, scikit-learn, okay? I'm not gonna get into the detail. By the way, it is implemented here. If you look at chapter 2 code, the algo is inheriting from my basic one. And here I just added this function in a nice, elegant way. And then we later on will use it. I'm not going to dive into the detail. I do have a Nuke encoder that's going to do adding more attributes to my database, okay? So let's move on to another topic which is extremely, extremely important. Many people don't have even a clue how important it is. Let's look at the data again. If you notice, you know, I have a housing median age. On the other hand, I have total rooms. The scale of the numbers are totally different. If I just run a regression, you know, this is something that most likely have been skipped when you studied in your statistics class. If you just run a regression, of course, this one gonna have a smaller coefficient, or this will be more dominant than this one just because the scaling is different. Well, even this one, look at the scaling. Those are huge numbers relative to this column. So what you really would like to do is to convert all the columns to have the same proportion. How do I do that? There's two very common methods. One is known as a min-max method, and the second one considered as standardization. And what does it do? Min-max is very simple. Let's say implement it, let's say on this column. In this column, I go and check what is the smallest number. Then I check what is the largest number. So I know all the numbers are between the smallest one to the biggest one. Now, if I take the difference between the biggest to the smallest, I get the range, okay? Now I take, let's say, this number, I will subtract the minimum, and whatever I get, I will divide by the range. Let's do it in Excel, okay? Let's do it in Excel. It's really important and very simple. Okay, let's look at this column, okay? I want to convert the 880 according to the min-max method. So I take the largest number, I'm just making it up. The 380, the largest number turned out to be, just take the largest here. Seems like 1966, no. In fact, this one is higher. Let's take that 70, 99 is the largest number. And let's say that the smallest number, see if I can get a small number here. Let's say this is the smallest number, 696. 696. Okay, what is the difference? That's the range. Like this one minus the other one, I get the range. Now I want to convert this one based on this method. How do I do that? I will take the 880, I subtract the minimum number, let's put it in parentheses, and whatever I get, I will divide it by the range. And if you really follow, this number always will be between 0 to 1, okay? It will always be between 0 to 1. In fact, if you realize 880 is very close to the minimum, that's why we're getting a very small number, okay? So min-max, your numbers were going to be converted to numbers between 0 to 1. So you will have a column between 0 to 1. You do the same things for each one of them, all the numbers turn to be between 0 to 1. That's one way to standardize the data so they will get the same magnitude as others, so we don't emphasize one variable over the other one. That's one method. The second method, called standardization, very simple. I take every number, first of all, I calculate the mean. Stage number one, I calculate the mean. Let's say I got a mean, I'll do it again in Excel. I calculate the mean. Let's say I got let's say for the same variable, let's say we got, I'm just making it up, 1100. That's the mean, okay? And then I would calculate also the standard deviation. Let's the standard deviation was 350. I'm just making it up for this column. So how do I convert the number 880 according to the standardization method? I will take 880 and from it, I will subtract the mean. So I think I better put a plus equal. And then I will do 880 and I will subtract from it. I will subtract from it the mean, okay? Close parentheses, and then I will divide by the standard deviation. One more time, how do I convert the 880? First, I will subtract the mean of this column, and then I divide by the standard deviation of the column. By the way, this is different than this one. Here I can get numbers, even large numbers, yeah? And they can be negative and positive. But one thing is really cool, it's the mean of those numbers will be always 0. After the conversion, you can do it at home. It's a good exercise that this one always will be a mean 0. So all the columns will turn to be with a 0 mean, okay? But the standard deviation will be different, okay? Good. By the way, the standard deviation after the conversion is always will be equal to 1. That's an easy proof you can do. I will leave it to you. But so let me sum it up. In standardizations, you're converting every variable in such a way that every variable after the conversion will have a 0 mean and standard deviation of 1. Okay, that's what you do in standardization. Very common, by the way, this is very common. Okay, and by the way, this one has its own problems, and I will leave it to you to read in a book. It's you know, if you have a very big outlier, it will make all the other numbers very small. Okay, so this is a very common one to deal with that problem. And there is also a whole topics of outliers we're not going to go into in this course. It's more advanced course in machine learning. But just be aware, this is really two common ways, and this is more common, I would say. Okay, let me take a pause and hear and see if anybody has questions. Please go ahead, guys. Anybody? Hello?
I think we're good.
You
No,
good?
we're
Thank you.
Good. Yeah.
Good, good. Thank you. Okay, I'll move on. So we talked about scaling, very important topic, but here is the important things. Last time we talked about it when we have the data, when we had this data, okay, we said we're going to take the data, we split it to two databases in a way of rows. We took 80% of the rows and we call it that our database to train a model. And 20% we said we'll put aside and we will test if the model will be able to predict. That's what I said last time. Today we will understand exactly what I mean by what I just said now. So we split the data to a training database. It's 80%, for example. It's very common. Sometimes people take 90% and keep only 10%, depending how big is the data set. But we take the data set. We're not looking now at the columns. We're looking at the rows. We take 80% of the rows and we call it the training data set. And we take the other 20% and we said, we're going to use those ones to see how good is the algorithm did in learning the relationship between those columns and the columns of the housing values. I think this is the one, okay? We want to learn from this one and all the other columns. Can we explain this column? So we take 80% of the rows, we learn the connections, and then we're trying to see, can we really say about the 20% we kept aside? So we implement, we predict based on the data, and then we'll see, is that close to we really see in those 20%? I will explain that one more time when we get there. So we divided the whole things to two databases. So just a comment, and that's a very important comment, when we do the scaling, the min max, we don't take, as I said before, in fact I misspoke, I do only the min max on this column only on the 80% of the rows, and then I will do the whole calculation. After I know the min max, I will implement it also on the test, but I don't calculate the min max range again. Okay, so that's really a very important comment here in the book, which I think it's worth noticing. Good. So that's just really the meaning of that one. Okay. Let's move on. What is a pipeline? I won't kill you on that, by the way. You notice that so far we talk about imputation for missing data. We talked about converting some data categorical into one hot array, blah, 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 and a lot of steps. There's a lot of steps we need to do. And if you try to keep track of all of that, you will get lost. So in that library, somebody have developed beautiful, it really is a nice work. They open another component called pipeline. Pipeline really allows me to stack all the steps together. And from now on, instead of having to think about each one of them, I really can forget about it. All what I care is that I have a new component called NumPy line, which I created. I already defined all the steps. By the way, this is the customized component. This is the imputer. We start with the imputer. We added more variables. Then we scale the variables. Okay, we scale the data. And then after we do it, all those steps, we don't want to go one by one. We just like to put them together. And pipeline is just a nice, simple, it really is a very simple component, that allows me to add all those steps together. And from now on, I can just take one line of command, tell him, please take this data and give me data and process all those steps on the data. Now I have data ready for machine learning. So one more time, pipeline, it's a component that allows me to stack several steps in the order I need to prepare the data for machine learning. Okay, very important component. Then there is another component that goes one step ahead. By the way, this is explaining to you how you build up a spatial a special, there's another special component, okay? Let's call it selector. I won't get even into that. This really allow you to take a NumPy array and convert it to a data frame, which is a very simple component, by the way. If you have a good eyes, okay, all what it does, it's really is converting it, but the other way around. It takes a data frame and convert it to a NumPy. This is really the only thing that does the work. All the rest just make it nice to work as a component inside a pipeline. Okay, I won't really require to know that, but just think about it, that when we got last time, if you remember the scaling, I didn't really say it explicitly, but it's written here. When you get the data from the scalar, it's bring it as a NumPy array, and if you want to convert it to a data frame, you need to do some more. So you can build up your own component. Again, I won't kill you on that, and I won't require that you know. But just be aware that there is a nice component that does data frame selector, meaning it's turning from a data frame into a NumPy array. So if you plug into the pipeline, when we have all those stages, so I misspoke before, this one is expecting for me a NumPy, so I just want there's another component you can build up and add it to the beginning here that automatically will take a data frame and it will do the work on converting to a NumPy, and I can say the hell with it, I can forget about it. Okay, and this is a really smart people. This is the way smart people usually work. You focus, you get it done, you put it in the right place and forget about it. So that's really what I meant when I talked about this one. If you really get into this work, learn it one time, implement it to what you need, and then you say, well, I'm going to take this component, I created it, now I forgot how I did it, and I'm just going to edit in the beginning. And all what it does to make sure that the imputer will get a data frame, it will get a NumPy instead of data frame. So the NumPy pipeline I will give it a data frame, but internally it will take care of it. So I don't really care about it anymore. So I know from now on, I have one component, I will give it a data frame, and he's gonna do the whole work that I need to do. So it will get me the data ready to put it inside a algorithm. Some things, by the way, you can make as many pipelines you want. And this pipeline, by the way, it's structured to take care of the column, the label one. So we made a pipeline to take care of all those columns, add more columns, scale the data, everything is perfect. The other one takes a categorical one and turn it to one hot array. So this is the second one for the categorical. This is for the numerical. By the way, you immediately can see that almost always you will go through this process in almost every project in machine learning. So this is a classical one. And then finally, you'll say, yeah, this is nice. Can I shrink the whole things to one thing? The answer is yes. There's something called feature union. All what it does, you can take those two pipelines, combine them together, and now I'm done. Thank God, you can breathe. Okay, now I have one component, and the only things I'm putting in is the housing. And remind you, what is this one? This is a data frame. And the beautiful part of it, after it goes through this full pipeline, and I can forget about the whole detail. I know that I'm giving him a data frame with this data that come from Excel, literally reading Excel into data frame. It's very simple. There is a function that read data from CSV or Excel. I read the data from the Excel. I don't really want to even remember how I did it. I only take that one that I read into data frame. I put it inside here. Bingo. I get data ready for my algorithms. And that's where you want to spend your time in machine learning. But frankly, if you don't do this right, you'll get garbage. And that's what happened to a lot of people. They do those ones too fast. Don't. Spend the time, build it up the right way. By the way, if you look at my code, I'm really never really spend any time. By the way, if we have time, I will introduce you to another project that I'm building, and you will see this is a real life project that I'm doing for article that I'm writing. And I'm building it up just like chapter 2. And chapter 3, you will see we're repeating very similar. We'll add some more stuff. But basically, this component does all this work. And the only things I have to remember is what this one of those functions does. We'll see in a minute. By the way, you see, set a pipeline. I was so lazy that in the code itself, I define the pipeline and just shift it to the code, and it does the work. I'm not really asking you to understand fully what I just said now. Clearly, it's very hard to understand what I just said. But just to summarize, those are the steps that usually we go through. I wrote some question in Take a Test to what I expect you to know for the exam, okay? And you know that all those steps eventually, up to this point, preparing the data to choose or train a model. And now we're getting to another stage. How do I choose which model to use to predict housing values around California? That's our next step, now that we're done with data preparation. Okay, you study statistics, and the first things come to you. And by the way, let me just open it up. Which algorithms did you study beside linear regression? Did you study anything beside linear regression? Is that ringing a bell of linear regression at all?
Yeah, we touched on it in statistics briefly.
Okay.
First year also, like a while ago.
Here is the good news. You know, if I were to teach you statistics, I will never teach you the way I was taught. Because the way I was taught, it was when everything was solved analytically. Those days are over. And frankly, as a machine learning person, I don't really care about the detail of any algorithm. In linear regression, people spend books and analyzing the data and how to check if the assumption's correct or not. I'm as a machine learning, I really don't care. Somebody give me a black box and write on top of it, linear regression. I said, thank you. Another guy comes to me and said, I have another box. The name of that box is decision tree. There is an algorithm called decision tree regression. I said, thank you. And now my choice is, should I choose the linear regression or should I choose the other box? What insight I really don't care. A machine learning person usually don't care. He likes to find which one works the best. And now we need to develop a criteria to say, this box that called linear regression does better job or worse job than the other box. And that's what model selection. We want to select the best model. So we need a criteria. And the logic says that which models will I use? The one that will be able to predict best. Okay, so our criteria will be which algorithm or which box predict better. And that one we will choose. Now let's take that one in brackets two pieces. We have two boxes. We have a data set, which we split it to two, training set and test set. We take the training data set, we put the data into each one of those boxes. Everybody follows? So we have two boxes. To each one of those boxes, I put inside the data, the training data. Somebody wrote the code, and I don't really care even how he did it. I just know one thing. It tells me that after he learned from the data, each one of those boxes has the ability to predict the value of a new row. Meaning, if I give him another data, he will know to predict what will be the value in California. In another word, I took 80% or 80% of the districts in California. I give it to those boxes. They learn the relationship between all those variables to value of houses in California. Now I have another 20% that those boxes haven't seen before. So now I tell them, can you please tell me on those 20% districts, here is all the parameters, all the variables, but I'm not going to tell you what the value of the houses in those districts. Can you predict now on those 20% what will be the house value in those districts? That's the predictions of those two boxes. Which box it will be a better box? The one that will predict as close as to the real values which I know. That one will be the best model. That's the one I want to choose. Okay? That's the criteria. Now, how do I choose? You know, I have a lot of districts. 20% of the districts in California, it's many districts. So some districts, the box, I call it a box intentionally. It really is an algorithm. Could be a linear regression, could be a decision tree regressions, and others. But I call it a box. And some of them it will predict good, and some of them it will not predict good. So how do I take an average to all of that? What we usually do, the criteria called mean square errors, meaning I take the difference between the predictions to the actual. Again, I take the difference between the predicted value to the actual. I square it. Whatever the value, I take square, meaning I multiply it by itself. I take the average for all those districts, okay? And then I take a square root. I don't really care. You know, now that you heard it, you can forget about it. You just need to know there is a function that does all of that, okay? And all what you really need to is I'm getting the data training to those boxes, and each one of them eventually gonna predict, and each one of them has an index how well they predicted. And what I really need to do, I will take the box that predicted the best. Very simple. The detail, it's nice, you do it one time and you forget about it, okay? So let's look at it. Okay, after we got the data, we have, by the way, you see it's the same library. This time we're just importing linear regression. And on the linear regression, very, very simple. We just, basically after we use the transform of the data, we'll have the data, this is ready, and now I can go and use that data inside the regression. So this is really the whole code. And in a minute, I will show it one more time. We take the training data and we basically put it inside. This is the first line to create a component to run a linear regression. So you can forget about the whole course in statistics because somebody have written the code in one line. This is like building up a component that know how to deal with linear regression. All what I need to give him, it's all the data, not including the housing values. So I take this table, it's just like taking this table. I take the median houses by itself, because that's what I try to learn about. And all the other columns, I put in another table. So this table, this one, it is all the columns, not including the column of the housing value. And the housing value, I put it right here. Bingo, I run a fit, and he already ran the regression and find the coefficient and everything. And honestly, as a machine learning person, I don't really care. All what I want to do is now to ask him, can you tell me, if I give you some record, and that's what this code does, it takes like 5 records. 5 record means it takes 5 rows from here. It takes 5 rows. It doesn't give him the house value. It's give everything beside this column. So I take 5 rows. I tell him, you know, I'm transferring that according to what we did in the pipeline, but that's a detail. And then I tell him, can you predict, and this is an important line, I take the linear regression component and I ask him to predict on these 5 rows. And let's see how well he did. So according to his prediction, this should be the housing value in those 5 districts. Now I can compare it to the real one. This is the real one. So the difference between the two, it's indication of how well this algorithm did. So the further those numbers will be from each other, the worse is the algorithm. In this case, the linear regression. So that's what we really usually do. And you can see there's another component called mean square error that does automatically. It takes each number, takes the difference, it square it up, it takes the mean, and then take a square root. And I don't really care, by the way, this is doing it manually, but there is a nice one that does it automatically, the whole things, okay? So basically, what I'm ending up is I'm using some linear regression, is learning from the data, I give him to predict, and I check how well he predicts. And this is like kind of an index, how well he predicted. The lower the number, the better it is. So far, so good? Yeah, anybody? Is that clear, guys?
Yeah.
Wonderful. Now you guys help me. I'm a machine learning, and somebody gave me another box called decision tree regressor. It's the same way I just building up a component just like linear regression. You probably never heard about that one. By the way, this is a really beautiful one. It's like decision making based on, you know, for example, if people are rich, you know they're going to have a high value house. If the people are poor, they're most likely going to live in a smaller houses, okay? So decision tree take every variable and try to divide the samples. I won't get into that too much, but you really don't need to care either, okay? This is a beautiful, but that's for a different course. So, but I don't really care, I'm a machine learning. All what I care is to find if somebody have written a nice code that can make my life to make money. Let's put it this way. And is decision tree regressor is better than linear regressor, I just do the same steps. I define linear regression here. I define decision tree here. I do a fit. I did the fit here. I do a fit here. So this, it's based on the same structure of scikit-learn, so they work exactly the same. So that's the way I train another algorithm, then I know nothing about it. Most over, I just implement the same things I will predict. You see, I have a predictions function, just like what we did here. We have the linear regression predict, exactly the same. So here I do, again, predict, very same steps, okay? And then I take the mean square errors from the sample. So I get an index, how well I did. By the way, here, I ran and I got a perfect predictions. This just seems like unbelievable. Somebody have written for me something so good that is perfect. He can explain the housing prices based on the other columns. What does it really mean? That if I give him all the other columns, he can predict perfectly the value of the houses on those districts. Seems like unbelievable. By the way, this is really a problem than really a true performance of an algorithm. What do I mean by that? And now I'm going into a very important issue. By the way, when we gave him some columns to estimate on, by the way, when we did the predict, we gave him some data. And if you see this data, if you follow up the book, okay, you will notice that this is the training data. This is that means he's learning from the training data and he's predicting on the same data. What does that mean? That he is a perfect, he learned the data very well, but he only learned the training data set. That means he It found the connection between every row in the 80% of the data. But that's not really the criteria we want. We want to know how well it can predict on data it never seen before. So we would like to perform these predictions for both of them, the linear regression and for the decision tree. We would like to tell him, don't predict on this one. We would like to give him a different data set, the test set. And as we will see in a minute, this algorithm won't do as good as we seems like when we give him the same data. Usually, many algorithms, when you give them to predict on the same data they learn, their error, that's what we call as exploration error, it's usually very small, okay? But the predictions error would be very high. So most likely in this case is like what we call the algorithm is overfitting. It's really learned the data so well, and it found a very sophisticated way to explain every number in the data, training data. But when it's trying to predict other data, usually it will get a problem. That problem known as overfitting. So in this case, we say decision tree is overfitting the data in the training data set. And the criteria are supposed to be, let's do the prediction on data that none of those two algorithms have seen. And based on that, we will choose which one is better, okay? So that's what really should be, but I will take one step and then we're almost done for today, what I wanted, and then I will go for what we're going to do next time. One more thing before I will dive into this one, I just really want to explain something else called cross-validation. That's another concept, very important concept. By the way, when we talked so far, we talked about 80% as the training data and 20% as the test data. Now you will say, why, Amos, you can do better. Why do you do only the 80 and 20? You can do, it's 5 times. What do I mean by 5 times? You know, if I have all the data, I took 20% of the test. So I teach the algorithm on the 80%, and then I test it on the test data. So then that's one time. Now I can take from the data set another 20%, different 20%, and use the other 80% to teach the algorithm, and again test how good it does. Okay, that's the second round. That's already 40%. So I can do it 5 times because I can have 20%. So I can run this one 5 times. So each one of that is cross-validation. What does that really means? I run the algorithm on 80%, use 20% to check how good it does. And since I can choose 5 times the 20%, that will be considered as 5-fold cross-validation. Why 5-fold? Because I have 5 ways of having 20%. If I divided the sample to 90% and 10%, then it will be 10-fold cross-validation, because I can do it 10 times. Everybody got it? It's a little confusing, okay? Or generally speaking, it could be K-fold. For my experience, 90% of the time, I rarely use more than 5-fold. I usually use 5-fold. That means 80%, 20% test. And I do it 5 times. And then I take the average of the measure of the how good is the prediction, and that will be my index, okay? So what we're going to do now, the next stage is to check, is the linear regression is better than the decision tree algorithm. We're going to use 5 times, and we measure how good each one of them did, okay? So that's really what the next step. Okay, instead of just doing it one time, 20% with the 80% and see which one predicted better, we will do it 5 times. That's what the cross validation means, okay? And when you do it and you see here the code and you measure which one worked better, in fact, you really find out that in fact, the linear regression did better than the decision tree. Meaning, the decision tree has a tendency to study too well the data. But then when you give him something which he haven't seen, he's usually not doing that good. So he's suffering from the overfeeding phenomena. And there's ways to fix it, by the way, okay? And that's not part of this course, okay? For now, it's just we trying to find which one is better. And we find out that linear regression, when we really checking who does better on an outside test data, the linear regression does better than the decision tree. By the way, if you follow the book and also if you follow my code, I really written here a very clean and a nice, I know if you look, this is really one row that tells run linear regression, do its cross validation 10 times, meaning the data training will be 90% and the test will be 10%. And all of that I managed in the component I gave you in the algo to do it one time. This is really cool that you get one line. And then here I'm just printing the results. And this is for the decision tree. And then you have one, I added another one, another algorithm, very sophisticated one called random forest. In the decision tree, we look as one tree. Just think about it, somebody had an idea, hey, instead of having one tree, just have many trees. And take the average between them. It's very sophisticated. That's really good in many cases. So it has a tendency of overfeeding, but it takes a lot of time to teach it. So it usually takes a lot of time to run, okay? Or even on our database, it takes a little time to run. So when you run my code, you will see it will wait a little bit until you get a response. But the nice thing is I'm running 3 algorithms. One I kind of learned in my first year or second year statistics course. The other one I don't even care who did and how does it work. I just want to know which one does better. And the criteria, which one has the lowest mean square error, okay? And the whole code is right here. Whoever wants to study it more deeply, you really have a step-by-step with a lot of comment that I put in. I'm not gonna go over the grid of or how to tune an algorithm this is really more advanced topic. It is in the book, it should be in the book in this place, but I'm not gonna go over that and I'm not gonna ask you or test you on that material. For me, it's very enough. And let me summarize, okay? Let me summarize, and I will start by saying the end, and I will go over the whole things, okay? It's very important to know how I choose an algorithm. I'm as a machine learning, I care about performance. And the algorithm that can predict the best is the best for me. And this is the one I'm going to use in real life. How do I test which algorithm is the best? I take the data and I split it. One part will be to train the algorithm, and one part is to test how good is the algorithm does. The one that does the best on the test is the best algorithm. Okay, that's the criteria. And how do we measure best? In here we saw one kind of algorithm, mean square error, but there's also absolute mean square error I mentioned last time. But that's a criteria of how close is the prediction. After I found which one it does the best, this is the one I use for real life. I just gave a little extensions. Then instead of doing it only one time on the training and the test, if we use 5-fold, we just do it 5 times. We always take a test, a different 20%, and then the rest will be for the training. So that's give us a better indication of which one is a better algorithm. That's really how do we choose which algorithm is the best. That's called model selection. That's the last part we just covered today. That's the whole thing's from scratch, the whole chapter. Let me go over, okay? But let's just me. This one I'm not going to go into that. This is really required to know algorithm a little deeper. So if I want to make sure that the random forest will work better, random forest has some parameters it depends on. But since you really don't know what random forest is, there's no point in getting into that. And that's really more advanced classes, okay? So let's add up, let's go all over the whole things we did so far. We got the data, to remind you, we got the data. By the way, this is all the steps. We got the data, okay? We analyzed, we looked at the data, we looked at the charts, we made the plot. If you remember, one of the first things we did, we looked at the data, and then we made some plot of the attributes. We looked at the attributes. In a second, it would come up. We looked at the data, we analyzed, we realized the data is not exactly normal distributions, etc., etc. So you can say that, and we said that's what we call the fat tail distribution. We might take a log. This one also, we notice there is a problem with the data. This data tells me that housing, most of them are in 2 areas from east to west. So we looked at the data really and tried to understand it. Then we took even a picture, look at the data, visualized it. And this is really a beautiful, that's called exploratory, analysis or visualizations. So you don't really have to be a statistician to realize that one of the most important things is how close you are to the ocean. The closer you are, the higher the prices are. And definitely proximity to the ocean has to be one of the variables to explain it. If my analysis will not bring the proximity to the ocean as one of the important parameters, then my algorithm probably is a very poor one. And then we went into a lot of other things that we talked about, data explorations. We noticed that, the distribution according to the income is not the same. And then we decided when we take the 20-80%, we make sure the distribution of the training data will be similar to the test data. So we don't just take 20% randomly, because many times randomly won't reflect the real one. So we wanted to make sure that the distribution of the median income of the sample in the training will be similar to the real one, and in the test and the training will be very similar. That's the next part that we talked. And then we talked about how to sample based on stratified sampling and not random one. And then we went to preparing the data. Those all one, you don't really see an output here, but the output you can see right down here, by the way. Okay, if you follow up, you see all the output right there when you choose the step. That's all the step we went until this one we're not going to cover. We today finish with select a training data. Let's really conclude chapter 2 in the level that I wanted. I'm very happy. In fact, as hard as it looks, and it is hard, it's not a trivial one. So please do go over that. There is a lot for you, which there are a lot of new concepts. I did put in the take a test. I try to put as many and I will add some more. Every week I add more. If you're going to take a test, this is the kind of questions I'm going to ask, style of question I'm going to ask in the exam, okay? So this really will help you and calm you down a little bit, but I'm not going to ask questions that you shouldn't know. And many times I put questions that help you to prepare. So please start to study. Don't leave it to the last week. Here, in fact, I'm asking a question right from the book using the same picture, okay? I might put that one in the exam and just ask you as an open question, and then you just have to fill it out, okay? So this is really a good, a lot of questions that I prepared. By the way, this one, I don't know why, but I put it in the middle, okay? Yeah, I'm just in the middle to complete. But up to 19, this is really something we covered today. You can really see, and I'm going to add more questions. So again, those questions are excellent to the level I'm expecting you to know for whatever we covered so far. What we're going to do in the next couple sessions, we're going to cover chapter 3. I'm going to upload a new version of the stuff that you did in the beginning of the semester. And I will put there some code for chapter 3. And chapter 3, as we go over it, will also be your project. What we're going to do in chapter 3, we're going to go really follow all the steps. I'm going to talk about really interesting, by the way, let's skip that for a second. We're going to, I started today's session by talking about it a little bit. I will expand today a little more. You know, people have different handwriting. And you might have seen some applications in which you can write by hand and it automatically will convert it to a, you know, it's like a machine written numbers, okay? So for example, if I write a 0 in any way of those one, it automatically will recognize it as a 0 and it will convert it immediately to a nice 0. If I write 1 in any one of those ways or similar to those one, it automatically will know that this is number 1. How does it do it? Anybody, you know, here is the question. I'm posing the question. Really, and you know, even if you get the answer wrong, believe me, I wouldn't know how to answer that question if somebody asked me when I started or took my own, when I started studying this topic. This is a hard question. How would you go about a question like that? How would you develop a machine learning process so that you will be able to make the machine to take these numbers, learn to identify different 8, different 7, the differences between each one of them. And then when Amos or any one of you write the number, let's say number 4 in some way, it will know that it is 4. How would I go about it? What is my data set? You know, in the previous questions, here we were given a data set. Is that right? So now, a simple question I would like to ask, what is my database? Is this, how do I take this kind of a picture? How do I take data like that? I'm getting a lot of zeros. By the way, this is just a sample. I will get thousands of zeros. I get thousands of ones. How that relate to this kind of a data organized this way? Well, honestly, that's a hard question. So let's start by asking ourselves, what is a number? By the way, what is a picture? When I take a picture of you, what did I really do? Anybody knows, by the way? By the way, this is touching a little bit to the big data issue. What is a picture? When I take your picture, what am I doing really? What the machine is doing? What the camera is doing? By the way, what is a colored picture? How is that made? Did you study that in any one of your courses? Anybody? Daniel?
Yeah, we did. I think a bunch of pixels. Is that what you're talking about, or I'm off?
Exactly. And how many pixels we have in a normal picture? We have about 1020, exactly. Most of the pictures, there's low resolution. We talk here about low resolution. If I look at a picture, we have like 1024 on 1024, that's about 1 million pixels. Only for one color, but colored pictures, it's made of 3 colors. So you really have 3 million, a little more than 3 million pixels. And now let's think about it. What is a pixel? Anybody knows what a pixel is? It's like a dot on the screen. Is that right? If I look at a picture black and white, let's say, like here I have a black and white, okay? But it's not exactly black and white because some places, if you look at the numbers here, it's a little gray. This one is a little darker, so that's more dark black, and this is more gray, okay? Some of them will be less dark, you know, it will be more gray, like this one, okay? So even in black and white, every pixel, it's every dot inside the picture, it's like a number between 0 to 255. 0 means totally black. 255 means totally white. And any number in between, it's how much gray it is and how close it is to a white. So if I look now, if I take now the number 0, the first one here, let's take it. You know what? It would be really cool. Let's do it. I like this one, and let me open the Painter. Okay, now I want to make a picture of the first 0. How do I make a picture of the first 0? I just simply go to the Painter. And let's say I'm making it in such a way that I'm getting 28 by 28. By the way, the database we will deal with, it's every one of those numbers, handwritten numbers, it's they are taken in a resolution of 28 by 28. It's like I have 28 by 28 pixels, okay? So now I have dots. I have 28 by 28 dots. I think it's 684 if I remember right. 28 by 28, it's 684. So I have 684 dots. Definitely the top one here, all of those one will be 0. Is that right? This is all will be 255, okay? When I get close to this area, this will be like about 200 because it's quite dark. And where it's gray will be more, you know, closer to 255 or vice versa. Doesn't matter. Okay, but the key point is if I had totally black, all the places of the black will be 255 and all the places of the white will be 0 or vice versa. It doesn't really matter. Okay, depending how I scale it. So a picture for me is, I can think about it, it's like 684 numbers. Does that make sense? This is pretty cool, by the way. This is really cool. For me, a picture of the first 0, it's in fact 684 numbers. And those 684 numbers represent the first 0. I can do the same things for the second one. I will get another 684, which in every place will be the density, how black is that pixel is. So now if I want to take, if I ask you in the exam, is this is the data set I'm going to use? The answer is definitely no. I'm going to take each one of those numbers, convert it to 684 numbers, so I have a long row. 684 columns. Each column and that row represent a different pixel. And of course, each row will represent a different number. So the row that represents zeros, most likely they will be very similar. They should be similar. The rows that represent 1, they probably should be similar. Okay, so our database going to be like this one, but it will have 684 columns. Each column represents a different pixel of the picture. That's pretty cool. You know, it took a lot of time for people to realize that. How do I take a picture and convert it to a data set that I can use algorithm, even linear regression maybe can do to identify numbers, which is really cool. Or use some other algorithms we'll mention, neural network I will mention next time, okay, or a session after. All of those is just by being smart person, taking that one and realize that this is really nothing but really organize the data in such a way that I can look at it as representing a number. Okay? Okay, this is really introductions to what we will do next time. I will upload a new version. I will send you an email. I will send you an email. I will send you notification of what I'm expecting you to do for next time. Questions, guys, before we end the session today?
No.
Everybody happy? Eduardo, are you happy?
Yeah, thank you, Amos.
How happy are you?
Very happy.
That's good. Daniel, you're
Thank
happy?
you, Amos.
I'm
Thank
pretty
you, guys.
happy,
Thank
honestly.
you, Rafael. Please go and see the videos again, okay? And look at my take a test so you'll be ready for the exam and don't wait for the last minute. Thank you, guys. Talk to you. And please send me any questions you may have. Have a good one.